Okay, I started another video, uh, and now we're going to write a code um, to do this new example using Newton's method. Okay, so let's open up our previous example, and we can just copy the whole thing maybe. I'm going to erase all of the code that has to do with plotting. And I'm actually going to erase the n and initializing the size of the vector x. And that's because we want to use a while loop, right? We want to continue the iteration until, oh, I have this little box here, until we have that g of x star is less than 10 to the 10. So we don't want a for loop. What we want is a while loop. So let's start with the root that we know is at 0. Now I'm going to say while. What's the condition on while? Okay. Oh, sorry. The first thing we need to do is change our function, right? We have x cubed minus 4x plus 1 and 3x squared minus 4 for my derivative, right? Those are the two functions. So going back up to my while loop, I want to do this while loop as long as the value of my function times, let's say, the most recent x, so like x, we'll call it k. We'll have a counter that starts with k is equal to 1, say. So it's the first step. That's the one that we've initialized with. So while that is greater than 10 to the negative 10, I'm going to do this while loop. And what do I do in the while loop? Well, I'm going to update. So k plus 1 is already defined. So I want, or sorry, k is equal to 1 is defined. So I want to define the k plus first term as the Newton's method iteration, xk minus gk over g prime k. And then I just want to make sure that I update my counter. So k is k plus 1. So I'm going to run this loop, and then I want to see what I get for the value of my function at the end, the final value of xk, and it should be something less than 10 to the 10. So let's see. So I run this, okay, I get a number that's 10 to the negative 12, and x is actually, I started at 0, and it goes to be about 0.241. If I try it with 2, I get some other number. Maybe I'll also do like x. Okay, it goes to 0.18, and if I do it at minus 2, it's like somewhere close to minus 2. So what I want to do is I want to make this code usable for all 3 roots, so I can plot them against the function I'm trying to find the roots. I'll add a little comment here. This is a counter, and this is just the initial condition. By the way, MATLAB has a squiggly line under x because it is unhappy that x changes size in every loop. There's not really a way to get around that. So in the while loop, I don't know how big it's going to be, so I'll just leave it. Okay, so here's what I'm going to do. I want to keep the final value of this loop for a bunch of different initial conditions. So let's call it a vector of ICs. I'm going to call it ICV, like a vector. I want to put in 0, 2, and negative 2. Oh, I guess I could do this in a for loop, but there's only 3, so I'm going to do it this kind of brute force way. I'm just going to define some variable, call it roots. It's an empty matrix. I'm going to run this iteration for the initial condition at minus 2 and say roots, the first term is going to be x and, which in this case is whatever it is. Okay, that's the actual functional value. And then I'm just going to recopy this. Not like the most elegant thing, but it gets the job done. And I think that that's really kind of the important thing here. So I run it with the initial condition at -2 up here in line 5. And I get the first root. I'm going to do 0 as my IC. And then that's my second root. And I'm going to do +2 as the IC. And that's my third root. Let's run this whole code. Now what's roots? Okay, 3 numbers here. And now the last part, number 3 of the class exercise, says plot. So make a little separate thing here that says, well, just one plot. So I have a figure. What I want to plot is the function. So I want to choose a bunch of x values and plug them into the function for g of x. So I know that the roots are going to be like from somewhere around -2 to +2. So I'm going to make this -3 by steps of 0.1 to +3 as the input. And let's say y vec is my function of x vec. So I get a bunch of y's. Then I can plot x vec versus y vec just as a line. The points are pretty close together, so I'll just connect them with lines. I'm going to put on a grid and hold it on. And then I'm going to plot the values of the roots. So the roots are the x values, and the y values, that's a 3 by 1 vector. The y values are a bunch of zeros. And I'll plot those as red x's. I'll make the line here blue. Oops, I need one more apostrophe. Awesome. Let's see if it runs. It does not run. Why does it not run? It doesn't run because it doesn't want to run my function. Because the way that I've written my function down here, and I kind of made mention of this before, assumes that x is a scalar because I have x cubed. If I want to put a vector into here, it's totally fine. It'll output a vector for y, but I have to explain to MATLAB what do I want to do when I say raised to a power. So I'll just do a dot exponent, which means element-wise exponentiation. I don't have to do it for the derivative because I'm not using that for the derivative, right? I'm only running through a scalar in the iteration. And then that should run. Let's see. Right on. Now I'm sharing, let's see, what am I sharing? I'm sharing MATLAB, so let me share the figure. So here is the figure that we made. So you can see the blue line. Move this in case you can see it. The blue line is the function, and then the x's look really close to the x-intercepts here, right? So it suggests to us that, yeah, we're doing the right thing. Yeah, great. So an extension of this work could be that you make this function more general, where you input into MATLAB the function and its derivative and the tolerance, like 10 to the -10, that you want it to do, and you want to see what the roots are, you could do that. But I think it's okay not necessarily to do that because MATLAB is not so great, like symbolically. So how you would input a polynomial, there's like different kind of formats. I think it's not a super great application for this. So I just want to make one more comment about this, about how this program works. And this is going to be about convergence. So I know the roots are where they are, right? So what are the initial conditions that'll lead me to the roots? Well, all initial conditions converge. So let's just comment out all this stuff for plotting and for root finding, just play around a little bit just here. So I've just commented out, you know, for the 3 roots, left the functions, and I just want to know how big I can make this. Remember the root here is -2. So I put in like -6. What will x end be? Oops. and I run it. Let's see. That's what's x. I put in, oops. Okay, so we actually have a mistake. So what's the mistake? The mistake is this number should actually be an absolute value, right? If I have a negative number putting in here, then I may think that I automatically satisfy this, right? Is that right? But it's going to be less than that. Let's see. I think this should be, right? Because -6, if I put in my x1 is -6, the functional value, my function of -6 is going to be some number, but it's going to be negative, right? Because it's going to be x cubed. There's a big negative number. So yeah, so this code actually needs these on all of the while conditions. Now if I run it, what happens? Okay, it looks like it converged to that same root. How big can I make this? Looks like it's always converging. It's not converging always to this root though, right? Like there's got to be some place where I stop converging to this root and I start converging to another root. Now if I put in -1, I pop up to the other root, the one that's near 2, right? So -1.25, oops. I go down to the root near -2, the -1, I go up to the other root. So not asymptotically convergent, right? It may not converge to this root, it may converge to some other root, and it may not converge, it may go up to infinity. In fact, let's take a look. So if I try the positive root, if I do 2, I go down here. If I put in like 200, oh, I guess I still converge in this case. What does the function look like? The function, oh, we stopped. Let's run it one more time. We'll get the function here and take a look at why that might be. Let's see, -2. Now uncomment all this stuff, including the plotting. Run it. So the slope here is 1. The slope here, is it greater than 1? It looks bigger than 1. I keep coming back down to this root, huh? Where are the roots? Oops, I forgot to change this IC. Here. One, 2, 3. Okay, so I guess in this case we're always converging to these roots, but not necessarily does it have to converge to any given root. And there are cases where it could go to infinity. So I guess that's all I have to say for the MATLAB activity for today. And that's the end of lecture 14. So thanks and bye.